This is the 31st video in a course on single agent search. And in this lecture, we're going to get into inconsistent heuristics. So for a lot of the course so far, we've assumed that we always have consistent heuristics. And we're going to do two sets of lectures on inconsistent heuristics to see what happens there. Inconsistent heuristics have a very interesting history because in the late 70s, people began to understand the impact of inconsistent heuristics. But at the time, it was thought that maybe these just sort of never arose in practice. And so they were forgotten, basically. And then what happened is actually, if we start looking at some of the pattern database techniques that were being used, in particular compression techniques, they actually started producing inconsistent heuristics. And that wasn't well understood, even when they were first happening, because inconsistent heuristics had sort of been forgotten as a field, but or as an area of study. But now we've sort of come back to a better understanding of them. And as a result now, actually, we have much better algorithms. And we're going to look at those. So we're looking at a series here where we're going to define inconsistent heuristics. In this video, we're going to look at the impact of inconsistent heuristics. And then in the next video, we'll look at some of the things that have been done to ameliorate the worst case behavior or to try and improve in practice. And then in the following that, we'll be looking at some other algorithms that have been developed, in particular the IBEX or budgeted graph search, and that'll build on some other work. So anyway, we'll get to that in a few lectures, but today we're just going to look at the impact of inconsistent heuristics. And what we're going to start with is well, maybe we should start with the definition of an inconsistent heuristic. So typically what we've expected to see is we've had a couple of different definitions, but typically what we've said is that for instance, the difference of heuristic between H and B, H A and H and B, has to be less than or equal to the cost of going from A to B, the optimal cost from A to B. And so this is going to work. This is the undirected definition. For the directed definition, the way I always write this is what we typically want to see is that the F costs are monotonically increasing. So if we go from some state A, where I have G of A plus G of B is less than or equal to the next state, which is going to have a cost, not G of B. Okay, so G of A plus H of A is going to be less than or equal to G of B, and I'm going to write actually G of B as G of A plus the cost to go from A to B plus the heuristic of B. And so what we're going to see here is we have two G of A's, right? So H of A has to be less than or equal to the cost of A to B plus the heuristic of B. Okay, so this says that if we have this property, this is consistency, then what's going to happen is that our heuristic values will always be non-decreasing. And so generally they're going to be monotonically increasing, where monotonically increasing actually contains that case of the value staying the same. Okay, so if we're inconsistent, then this isn't going to hold. And this is the case that we're going to look at a little bit more commonly because we're mostly going to use undirected graphs here. All right, well, at least initially we'll do this. So let's create an example and see what happens with an inconsistent heuristic. And then we're going to ask what happens in general. So we're going to have the start here. We're going to have a state A, we're going to have a state B, and then we're going to have a state G over here. And the idea is that I'm going to create a path, which is a shorter path. So this is the shortest path to get to B. But we're going to block this with a heuristic. So I'm going to write heuristics next to a state, and I'll write them in blue just to make them clear. So heuristic of 6. We're going to have a heuristic of 0 here. We're going to put a heuristic of 0 here. And we'll put a heuristic of 0 here. So we'll put a heuristic of 0 everywhere, except in this one state right here, where the heuristic is going to be very accurate. And so what we see here is this expensive path has 0 heuristics all the way along that path. This less expensive path has a higher heuristic value on it. Okay. Oh, and I need one more cost in here, but since I need the heuristics to still be admissible, so from A, the cost here does have to be 6. So we're going to put an edge cost of 5 right here. Okay, so what happens in this case? Well, what happens is we're going to expand S with, we'll write here F, G, and H. So we're going to expand F with a F cost of 0 because it has G of 0 and H of 0. We're going to generate A and B. A has a G cost of 1, has an H cost of 6, so it's an F cost of 7. And actually, let me number these just for the sake of clarity here. So we did this one first. So there's B now has a G cost of 3, a heuristic of 0, and an F cost of 3. And so the next state we're going to do is B with a F cost of 6. Sorry, an F cost of 3. Sorry. And so we're going to, after that, we're going to generate G. Okay. And so G has a, we don't find it, B doesn't give us a shorter path to A. So we're going to generate G with a G cost of 8 and a H cost of 0. Sorry, H cost of 0. And so this is going to be 8. And now if I have a choice of what to expand, I'm going to choose to expand A before G. So I'm going to do A third. And now what's going to happen? I'm going to regenerate B. And so this is the interesting thing that's happened. Actually, if we look here, what has happened? Our F cost, we started out with an F cost of 0, and then F cost of 3, and then an F cost of 7. But now what's going to happen is we're going to put another copy of B. Basically, what's going to happen here is we're going to have to take B that was on the closed list because we've expanded it. We're going to have to take it off the closed list and put it back onto the open list. And when we put it back onto the open list, it's going to have a G cost of 2. It's going to have an H cost of 0. Oh, sorry, H cost of 0 is here. Sorry. And so now the total F cost is going to be 2. And that will be my fourth node expansion. So what we see here is that F cost 0, F cost 3, F cost 7, and then F cost 2. So the cost went up and down. And sorry, I didn't show you here, but here we have the inconsistency. We see that the cost here, the heuristic is 6. The difference in the heuristic is 6, but the edge cost is only 1. So that's an inconsistency. In fact, this is inconsistent as well because the difference in the edge cost is 1. A difference in the heuristic is 6, and so the difference there is greater. Here, this is fine because the difference in the heuristic is 0, and that's less than the edge cost. And so it's only here and here that we're going to get into trouble. And this is still consistent right here. But what's happened here is we've been caused to expand B 2 times. And that seems like it's a bad thing. And in practice, it actually is. And so what we're going to do for the remainder of this video is we're going to show just how bad this can get. And so that'll be, for this video, we're going to go through an example. This example is actually available on my website. I'm going to put a link to the demo below it, below the video down below. And I encourage you to go look at that example and to scale it up. And I'm going to go through here. Well, we're going to write a bunch of things down. We'll see what happens. And this will give us an understanding of how bad things can get. And then you can go watch the video or you can watch it now. And then in the next video, we'll talk about fixes that have been proposed to it. So hopefully this video will be a little bit shorter, but I've taken the example from the web page and I've put it right here so we can see it. And what we're going to do is we're going to label the nodes, and then we're going to write the same thing here, F, G, and H, and we're going to look at what happens as a pattern. I actually encourage you that if you'd like to make sure you understand this well, what I would typically do if I was not doing a video is I would ask you to go ahead and try to do this on your own and see if you could write out everything that happens here. So, and then I would show it and we would do it together as a class. So let's go ahead and try this and see what happens. So what we start out is we're going to start out with a start state. The start state is A right here, and the goal state is capital G. These are the heuristic values on the side. And then inside here, these are all the edge costs. The edges are in gray. And so we're going to start with node A. Node A has an G cost of 0, a heuristic of 23, and an F cost of 23. And so, of course, we're going to expand A. And then what we're going to put onto the open list? Well, we're going to put onto the open list, so this is going to be 1. We're going to be putting on the open list B, C, D, and E. And B is going to go on with a G cost of 1. And it has a heuristic of 13, so that's going to be 14. C is going to go on with a G cost of 6, a heuristic of 7, so that's going to be 13. D is going to go on with we're going to follow this edge right here, so that's going to go with a G cost of 9, and a heuristic of 3, so that's going to be 10. And E is going to go on with a edge cost of 11, and a heuristic of 0. So that's going to give me 11. So I added these up wrong here. So 9 plus 3 is equal to 12. Okay, so what we have here is, what we see is actually 11, 12, 13, 14, and 23. We're going to choose the minimum. So the next node I'm going to expand is going to be E here with cost 11. And after I do this, E is going to give me the goal. I won't write this down, but the goal is going to have cost 30, and everything else on here is less than that. And the other thing I won't show is we're actually going to assume that all these edges are directed going down here. So we're not going to get any of we're never going to go backwards up the graph here. Okay, so what do I do after I've done E? That doesn't give me anything else, but I'm now going to go ahead and do D. And when I expand D, what do I find? Okay, well, I've got it. I'm going to look at our successors, and the only successor is going to be E. And what happens here is this is cost 9, and this is cost 1. So overall, that's cost 10. So I've reduced the cost of E from 11 to 10. So I'm going to put E back on the open list. It's going to have a G cost of 10. It's going to have a heuristic of 0. And so it's going to have a cost here of 10. And so that's going to be the cost of what we have here. And that gives us that we're going to be expanding E next. So E is going to be, so that's the minimum, right? So E is the minimum of everything on the open list. So we're going to expand E again here. Okay. And after we've done E, then G is going to be updated slightly, but we're really not going to get to G till the very end. So just to point out here is the optimal path is to go all the way along here. So we're going to do D, we're going to do E, and then D, then we're going to go back to E. And what is the next best node here? Well, the best next node is going to be C. So next I'm going to do C, that's going to be number 5. And what happens when I expand C? So C is here with cost 6. I'm now going to get a path. Total path costs 9 to get to E, and a path costs 7 to get to D. And those are shorter than the ones we had. So I'm going to put back on the open list D with a path cost of 7. And D has a heuristic of 3. So this is going to be 10. And I'm going to get E with a cost of 9. E has a heuristic of 0, so E is going to have cost 9 here. So sitting on my open list is B, D, and E. And the minimum cost is actually E here. So E is going to be number 6 to expand. After I do E, again, I'm going to lower the cost of G, but other nodes, I'm not on the optimal path yet, so I can't go to the goal. And the next node I'm going to do is D. So this is 6, now this is 7. 7, so when I expand D, what happens? So I come down to D, but, oh, sorry, this isn't my path to D. My path to D is now 6 plus 1 is 7, which means now I have a path cost 8 to get to E. So I'm going to put E back on the open list with a cost of 8, heuristic of 0, the F cost is 8, and now the only thing on my open is 14 and 8. So I'm going to go ahead and I'm going to expand E. That's going to be 8. Okay, I can continue this process, but I will stop it here. As I said, you can watch it one step at a time on the video, but let's look at what's happening here. So we're going to do A. At the very beginning, we'll never expand that again. We can't re-expand it. But then what are we going to do? We're going to do A, and then E, and then D, and then E, and then C, and then E, and then D, and then E. And if we continued here, what we would see is we would actually do B to E, and then we would do B to D, and then we do B, D, E, and then we would be doing B to C to E, and then we do B to C to D, and then we would do B, C, D, E, and then we'd be done. So at this point, we've done half of the node expansions. We've done everything. Once we expand B here, then we'll basically redo everything that we did before a second time, except using B as the source instead of A as the original source. Okay. And so what we see here is the number of expansions here. I have 1, 2, 3, 4 nodes in my main area. I've done 8 expansions so far. And in general, what's going to happen here is I'm actually going to do 2 to the n node expansions. And if we look what's going on here, if we think about our paths, we can ask the question, what nodes are in our path? So the question is, do I have A in my path? Do I have B? Do I have C? Do I have D? Do I have E? And then I have G is going to be at the end. And what I'm looking at essentially is, well, A is always in there, so we won't really think about A. But I'm thinking about my paths that I'm creating here, where I put a 0 of whether it's in the path. And I'm starting out, well, I have to start out with something, so I'm going to start out with E. And then I'm thinking a path, like what nodes are on top of here. Well, so now I'm going to say, well, I'm going to go through D. And I always have to go through E, but I'm expanding D, and then I discover that I'm going to go through E. So I'm considering now a path that is D and then E. Sorry. And then I'm going to think about the path going from C, not going through D, but I don't know where it goes yet. So I'm just thinking about putting C into the path. And then I'm going to discover that that path actually has to go through E. And so what's happening here is I'm essentially getting a binary counter where I'm thinking about, essentially I'm getting partial paths. So for instance, E, all paths to the goal do go through E, but I'm thinking about partial paths going through C. I don't know where it's going to go yet. And essentially I get a binary counter here where I'm counting up over all combinations of all of these nodes here, of whether they're included in my path. And when I've counted through all of them, then I'm going to get 2 to whatever this number is, node expansions. In particular, E is going to be expanded every other node expansion. So this is every second, this is going to be every fourth, this is going to be every 8th, every 16th. This one only happens once. Actually, B only happens once as well. But essentially what we're getting is a binary counter here, and thus we're getting an exponential number of node expansions. So in the worst case, you may have heard that A star is optimal. We can ask that question. Well, the answer that we get is in the set of nodes. If we talk about the sets, even if we have an inconsistent heuristic and the set of nodes expanded, A star is doing the minimum nodes given that set. But if we're thinking about so that's true. This is true, but it's false in the number of expansions with a inconsistent heuristic. Okay, so this seems really bad. And in practice, there are a number of ways that we can solve this. And there's an algorithm that was designed called B. And we'll look at that algorithm just because it helps us understand what's going on in practice. And we'll see that that algorithm, along with actually some other ways of propagating heuristic information, are able to fix what goes on in this example here. So we can fix this example and do much better. But then we're going to find another example where actually we're going to be looking at an n squared behavior. And then we're going to take that n squared behavior and we'll be able, so we're going to have a set of lectures sort of getting down to what's the best we can do before very recent work. And then we'll be showing very recent work on the topic that gets us down to better than that, which is sort of n log c star, where n is the number of nodes in not necessarily in the state space, but the number of nodes that are necessarily expanded, something like that. So anyway, we'll look forward to that. We'll look to understand how we can fix this problem. We'll see where we can still get this worst case of n squared, and then we'll look at some other algorithms that can use to improve it. Okay, so hopefully you continue. And as I said, play around with the example, crank up the problem sizes, and then you'll really see the problem that's going on here in practice.